Quantum numbers. Here's a quick reminder of the meaning of the four quantum numbers. N is the principal quantum number. It represents the number of the electronic layer and therefore the period number of the element in question. L is always found between 0 and n-1, and it defines the shape of the orbital. M is always found between positive L and negative L, and specifies the directionality of the orbital, if there is any. Finally, S represents the spin of the electron, either positive a half or negative a half. With this information, we can see that it's important to always start by finding n, and then finding the other quantum numbers one after another, since each quantum number depends on the ones before it. Drawing the electronic configuration of an atom allows the visualization of the quantum chemistry of each electron. For example, here's the electronic configuration of magnesium: 1s2, 2s2, 2p6, 3s2. This is what we get when we draw the orbitals, where each arrow represents an electron. The purple number represents the principal quantum number, n. Here's a trick to find L. The s orbitals have a secondary quantum number of 0, p orbitals have a secondary quantum number of 1, for d orbitals L is equal to 2, and for f orbitals L is equal to 3. To find m, you just need to identify the values from negative L to positive L for each orbital. For example, the s orbital always has L equals 0, so that means that m must always be equal to 0. The p orbital has L equal to 1, so m for each orbital can be -1, 0, or +1 respectively. If we had a d orbital, we would have L equals to 2, so the orbitals would have -2, -1, 0, +1, and +2 respectively as m values. To find the spin, we just need to look at the direction of our arrows in the orbitals that we have drawn. If the arrow points up, we have a spin of positive a half, and if it points down, the spin is negative a half. To find the values of the principal quantum number, we need to find the electronic configuration of the atom: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Don't forget that transition metals are special when doing electronic configuration. Remember that the first digit of each orbital in the electronic configuration is the principal quantum number, n, and the number in the exponent is the number of electrons in each orbital. So by adding the exponents of each orbital with n equals 3, we get a total of 18 electrons with a principal quantum number of n equals 3. Here's how to find the answer. To find the m values for each orbital, we will first draw the orbitals. Note that it's important to place an electron in every orbital before returning to put a second electron anywhere. This is why the 3p3 orbitals are not full. They each have only one electron, instead of having 2 in the first orbital and 1 in the second. All the s orbitals automatically have an m value of 0. In the p orbitals, when they're full, 2 electrons have an m value of 0. The 3p3 orbital only has 1 electron with m equals 0, and this gives us a total of 9 electrons with m equals 0. To find this answer, we start again by drawing the orbitals. At the start of this video, we saw the electronic configuration of magnesium at its fundamental state, so just Mg. In this question, we're talking about the cation Mg2+, which is much more stable than Mg at its fundamental state. Magnesium 2+ lost 2 electrons to obtain its positive charge, so the 3s2 orbital is empty and disappears, and its electronic configuration is the following: 1s2, 2s2, 2p6. Only the s orbitals have an L value of 0, and half of these electrons have an s value of +1/2, giving a total of 2 electrons having L equals 0 and s equals +1/2.